and this is what this phrase means, they'll say point estimate. And it sounds like you're supposed to guess something and then point at it, but point estimate is really just another name for best guess. Based on a sample. We put it all together. So really go with me here. If I have a population that I don't know anything about, I can take somewhere there's a mu. Somewhere there's a mu for this population. Whatever it is I'm talking about. You guys with me? That's a weird phrase. You would never, somewhere there's a mu. It's not a Pokemon. And I don't know where this sucker is. I don't know what its value is. So obviously from the first day we knew the best way to get an estimate for what this is to take a sample. This chapter is finally putting everything we've learned so far together to give a better feel for what that estimate is. How good is it? So we take a sample and we get some X bar. More than likely it's going to be close to this. The larger it is and the more truly random it is, it should be pretty close to this. So part of what this confidence interval idea addresses is that idea, how close, what is close, right? So then we construct a confidence interval. We go up and down so much from that best guess. And really this mimics in real life. How long is it going to take you to get here? About 3 hours, give or take half an hour, depending on traffic. Right? Doesn't it sound like something we would say? Yes? Maybe? Of course, around here it's like plus or minus an hour based on traffic, but shit. So what we do, so this is the idea. The idea is so flippin' beautiful. There's a real one. We don't have a clue what the shit this is. We get a guess, we go up and down so much, and then we can say we're this confident. Based on how wide we made the interval, we are whatever percentage confident that our interval catches the real mean. So what does this mean computationally? Well, we take the guess, we go up and down this many, because these scores mean the number of standard deviations of these. So this is controlled by how confident you want to be, what the spread is, how big the sample is. It kind of makes sense. The bigger my sample gets, the smaller the error should get. The more confident I want to be, the bigger the error should get to kind of catch more shit. And then the more or less spread out my stuff is, that also directly affects how spread out my confidence interval should be. How do you guys do it? I never know if I'm over-explaining something. Most often students feel like I'm under-explaining something, so shit, I try to go over. So let's do, let's do this. The next thing we did a few examples of this. We'll do another example of this, a very quick example. And the next thing we did last time was we worked with, remember we started with this idea. We came up with this. And now we did it again and we came up with this guy. That's a cube trying to be a cube. Yes, sir.
Is that n the size of the population or is that the sample?
N is always size of the sample. Size of the group we're dealing with. All right. And if I had a whole population, I wouldn't need to create a confidence interval because I'd be 100% confident what the population information was. Yeah. Okay. By the way, in case you're at all curious, there are adjustments to these formulas for populations that are kind of smaller than we consider. To be honest, these theoretically work if the population is infinitely large. 300 million is close enough to infinity mathematically, believe it or not. Some of you guys are like, what do you mean close to infinity? But computationally so. But if my population was like 80, and I take 30, a group of 30, these are going to have to be adjusted a little bit because my population is so small. But we're not going to worry about that, okay? That would be like a stats 2 kind of thing. Just in case you were curious, there are adjustments if my population is smaller. Okay. So that catches us up to where we are. This is for me, obviously, where the standard deviation of the population is known, which still feels a little dishonest, but it actually does happen. There are situations where I know this. So if I have a whole population and I take a sample from a certain area, I could know the standard deviation for everything, which means it works for that area also. So then I would know this. Now, what happens more often in statistics is we don't know a damn thing. Right? You guys are like, yeah. Right. We don't know a damn thing. So what we're going to get into after we do a couple examples of these is what if I have to put an S here instead of sigma? What's going to change? One thing changes. So let's do a couple examples with these, and then we'll get into that next level. Okay. Leave those up there. So, for example, we take a sample of 87 gross 1 students and find average number of units taken of 11.19, sigma known to be 4.28. Before I go even any further, can somebody tell me two things? One, this is going to be very obvious. Why is this normal enough to do something with? Yeah, n is 87 greater than 30. No big deal. What part of this, what idea behind this formula requires me to know that it's normal enough? What about the z-score? Do I have to have a normal distribution to calculate a z-score? No. But I need a normal distribution to take a percentage and make it into a z-score. Because what do I use to do that? Z-score chart, 11. Okay. Part of what we did with this last time, I don't know if you guys remember, is we talked about when is this situation normal enough? That's a different check. This one's easy. We've known this forever. We'll talk about this one in a minute. So I know I can do something because it's normal. It didn't say it's normal, but the sample size saves the problem. If this was 11, it better freaking say it's normal somewhere. Now let me just say this. I'm not evil enough yet. I don't know when I'm going to become evil enough to create a problem on a test where if you didn't notice it wasn't normal, you do a lot of work you didn't have to do. You guys know what I mean? If I put like 11 and it didn't say it's normal, the right answer would be, we can't do shit, and then you keep going. But it would be so evil for me to go, you didn't notice and you did all this extra work. I'm not quite there yet. Right? Give me a few more. 10 years ago I said, give me 10 more years, so maybe 10 more years. Find the 99% confidence interval for the true mean units taken by gross one student. This is exactly the way a problem would sound in the book, on a test, on a quiz, whatever. So let's do this one. Let's see. First thing I do for almost any problem, especially ones involving a known formula, is just summarize what the shit you know. Right? What do we know from all this? It's that I need the simple stuff. Sample size is 87. I know that. What else?
X bar.
X bar is 11.19. What else? Then you got this wonderful sentence here.
We got sigma.
Sigma is 4.28. So I've got N, I've got sigma, I've got X bar. Where does this dude come from? Where's that Z come from? Yes. How am I going to become 99% confident? What is the almost too nice to believe idea behind this? For me to be 99% confident that my interval catches something, I catch 99% of shit. If I caught 99% of the fish in a lake, what's the probability I caught a certain fish I wanted to catch? 99 frickin' percent, right? Do you guys, that idea is almost like, how does that belong in a math? But that's what math really is. It's a very fundamental idea, and you can see how it's captured by the formula. So these things, you basically have to be told what they are. This guy comes from how confident you want to be. So can somebody take a minute and figure out, don't say it out loud yet, what the z-score is for 99% confidence? You got the long cut and you got the shortcut. Today we're going to get an even better shortcut, believe it or not. More precise shortcut. So if you want to be 99% confident, you go out and you catch 99% of the stuff. How much is back here then? 0.5%, so 0.005. And if you look that up in the chart, we should get a little asterisk dude, right? Man. Some of you guys are helping me out. I like it. Now, as you guys are getting closer to the answer, I want to remind you there's that little baby chart too. Remember that? Little baby chart? In the bottom, I always forget, on the positive z-score side in the bottom right-hand corner. Do you guys see where it says confidence level? If you want to. Doesn't matter. 99 says 2575. If you do it in the chart, you get the little asterisk. It's 2575. I like it. Okay. Where's this idea caught by the equation? Then I want to go down and up. It's obviously where there's that plus or minus. That's why I don't put negative in the prize. The plus and minus is already built in. Don't freak yourself out. So the formula is this. Why is that piece there? Because that's the up and the down. So don't put negative 2575 here also. Sometimes people do that and get freaked out about how that works. You could. Totally could. Should be something you can handle. But it still freaks people out. Plus or minus negative, and they're like, how do all those signs work together? Same way as always. So now you just throw stuff in. So I get 11.19, give or take, 2.575 of these. Got it. Let's go ahead and try to do that. If you don't have a calculator, you might want to get one now because we're going to be doing worksheet stuff later.
Standard deviation equals you have times 2 half.
Wait. Am I doing a confidence interval for a percentage, or am I doing a confidence interval for a mean?
Confidence interval for me.
Yes, so there's no P's and Q's in this problem at all. Right? I like it. Anybody doing that error piece yet? Here's Riley, hold on. Let me give you wait. Let's see. Anybody got that piece yet? The error piece? I do. What do you guys get? Anybody? For the error?
1.18.
Yeah. So I get 11, let me put it over here. 11.19, give or take. $1.182. So in general, whatever the mean is, go out one more place with the error. So my best guess was 11.19. If I did include stuff around that, that would give a feel for where the real mean is. But I have to base that around that idea on something real. So I go out far enough to capture 99% of the data using these steps. That's what goes to construct this 99% confidence. It's almost too nice to believe. So if I subtract that, shit. What do I get? I get 10.008.
Yes.
And if I add it, I get 12.372. Okay. So now if you weren't here last time, you won't have a freaking clue what to do right now, but write the conclusion for that. Sure. Yes.
This formula doesn't seem to change for like the size of the population. Like if you gather the same data, you use the same formula for if the whole population was 100 versus a million.
So that's why I said what I said a little while ago, that there is a correction factor that's used for situations where the population is very small or relatively small.
The population's relatively small, or the population relatively small?
No. You don't need a correction for the population is large because the formulas are built on an infinite population. So if your population is relatively small, and what defines that is really a little bit of a leeway there. But if your population is relatively small, there's a correction factor. There is. But it's sort of like a next level thing. So I can't remember. I know in the other book that's used for this course, the Triola book that I used to use, they actually have a problem like the number 102 problem. And it says, here's a correction factor used for small populations, and they give it to you. But they don't make it part of what they teach. It's just kind of like a bonus problem in a way. But there is a situation, there is a correction for that. There is. All right, so what are you guys getting? How do you state this?
We are 99% confident.
Yeah, we are 99% confident. That what? The interval 10.008 units to 12.372 units. What are we sure about that interval? What's it doing? Contains the true mean, Ellie. Contains the true mean number of units taken by gross coincidence. Get out of there. It makes sense. It contains 12. What's special about 12 units? If you get any financial aid or anything, that's officially considered full-time, right? But there are students who come here and they only take one class. You know, they take one physics, exercise science class, right? I almost said PE. It would slap me. Sorry, guys. But then you have those students that take 20 some odd. You're like, what the hell are you doing here? 20 some odd units, right? Maybe some of you have done that before. Okay. Is everybody decent with that? You're always going to have to write that conclusion at the end. Because that's the big part of statistics. Is, oh, great, you got some numbers. What the shit does it mean? That's almost more important. All right. So let's do an example of the percentage problem, and I'll let you guys finish this worksheet out. What was the check? I'm not going to go into the whole explanation of why this is true, but what was the check to even know that I'm allowed to do this? Anybody remember? Yes, good. So the mean's got to be big enough so it's away from that zero wall. But also the means of failures has to be big enough so it's away from the other wall. So it's almost, again, I know I say this a lot, but it's almost too nice to believe. I just want to give it room so that it can grow and shrink. If it's too close to either of the walls, and what the shit are the walls? Well, the least you can have is 0, and the most you can have is n. So if you are too close to one of those two walls, you don't have room to grow and shrink. So these two just kind of put it more in the middle, and then it's going to be normal. It's going to be normally distributed enough to use that z-score chart. I like it. These problems always feel like they don't give us enough information because they don't really have to tell me much at all. So let's say we talk to 412 registered voters. 305 of them wish the election would just be over already. Find the 90% confidence interval for the true percentage of all registered voters who wish it was over already. Right? So really, it kind of, I don't know if you guys agree with me or not, but to me, it always felt like there was so much less, there's less information given because I don't need as much. So somebody help me out, especially if you weren't here last time. You hopefully are saying to yourself, what the shit is sitting up here? What is that? What is that? How do you say that symbol? What is that symbol? P hat. I like it. All right. Again, probably not some clothing you want to wear, but why is it wearing a hat? What is that supposed to signify? It's from a sample. I love it. Kick ass. I like it. Right, it's not just a fashionable variable wearing its little hat. It comes from a sample. Sort of like, I like the fact that like X has a bar on it, P has a hat on it. That means that they're from samples. Well, so how do I get this? From what I've told you, how do I get this?
X over N.
Yeah, it's going to be the percentage I see from my sample. So what I see from my sample is 305, wish this out of 412. I like it. Nowadays, people seem to understand percentages less and less, but just the fundamentals of getting a percentage shouldn't be horrible. So p hat is going to be 305 out of 412. Whatever the hell that is. 740?
Yeah.
Neat. I'm so easily amused. That has a very important little thing in it. Remember I said the P hat Q hat always has to be at least 3 decimal places. So again, make everything 4 places if you want, except for z-scores, and you're golden. So what's Q hat? 0.26. Is this normal enough? Who remembers a shortcut? I mean, what is n in this problem? 412, not 305, right? It's 412. And what am I supposed to check? Let me put little hats on these guys. I'm supposed to check n, p hat, and q hat. What's 412 times this? 305. Right? So if I just see the number of successes, 305, well, that's definitely, NP hat is 305. Now you could take 0.740 times 412. You'll get 30 something ... Okay, maybe. So what's NQ hat? The rest. Well, there's 412 total, so what's NQ hat? How many are failures? 107, right? And those are both, I think this book says greater than or equal to. Some books say greater than, some books say greater than or equal to. Okay. Those are obviously both bigger than or equal to 5, which means this sucker is normal enough to do the confidence interval. I like it. We got everything we need except for one thing, and of course, what's that one thing I need? I've got p hat, q hat, obviously. I've got n, obviously. So the only thing I need is z. And where does that come from again? Always the same place for these guys.
Chart.
From the chart based on my confidence level. Is this one in the little baby chart? I can't remember.
Yes.
Just to remind you, just in case you have a teacher like me that's going to give you something that's not on that baby chart. You figure out how much is in one of the tails, you look that sucker up. In this case, you would get negative 1.645, so this has got to be positive 1.645. I like it. That's how far I go to catch 90% of the information. So if I go that far, I'm 90% confident I caught a certain thing. Okay. So now you just got to throw everything into that formula. Take some of this stuff away. Leave that there so I don't forget what the hell we're doing. So p hat was 0.74, give or take 1.645 of these. I'll give you, yeah. 0.74, 0.26 divided by 412. The biggest mistake is to put 305 there, but that's not n. N is a total. Figure out what the error is. Haha, it's not so bad. What do you guys get? Anybody get something for the error?
0.035.
Yeah. 0.355. Let's make it 0.36. So then my little interval is going to be 0.7. What do you got, Jeff? 0.4? Yeah. 0.776. Is that cool? You subtract that, add that. All right, so when you get that error, then you just subtract it from this, you add it to this. Cool, I like it. You guys are keep me honest. Let's see if I could use this. So we are 90% confident. 2% is all under. That what? We're 90% confident.
At the interval, 0.07.
Good. At the interval?
0.04.
Careful.
Oh.
In this case, units for percentage problem are just actually making these into percentages. At the interval 70.4% to 77.6% does what?
I want it to be over.
Contains a true percentage of all registered voters who wish the election was already over. Yes?
You see polls online, what's their confidence interval?
Unless they state otherwise, it's 95%. That is the standard one to create. Gallup uses 95, but they also tell you, hey, we're using a 95% confidence interval. That's the standard one because we accept 5% to be small enough of an error to feel pretty good that that's our error. If there's a 5% chance you're wrong about something, that's pretty good. Shit. Okay, maybe. There are situations where other levels of confidence are required for certain reasons, but the standard one is 95%. Okay, I like it. So, if you haven't done this already, on the other side of the sheet we did last time, there's a problem related to percentage confidence intervals. Go ahead and do that. If you need a calculator, they're up here. Notice I was a little bit evil on this one, but not really. I want a 96% confidence interval. Just 'cause.